This question was asked from the GATE Physics paper 2021. This is a MCQ type 2 marks question, and this question was asked from the topic quantum mechanics. The question is, consider a particle in a one-dimensional infinite potential well with its walls at x equals to 0 and x equals to L. The system is perturbed as shown in the figure. So in the figure it has been shown a particle in a one-dimensional infinite potential well. In addition to that, we have a perturbed potential which is varying linearly from x equals to 0 to x equals to L. At x equals to 0, the perturbed potential has value 0, and at x equals to L, the perturbed potential has the value V0. We have to find the first order correction to the energy eigenvalue. There are 4 options given. First option is option A, V0 by 4, option B, V0 by 3, option C, V0 by 2, and the last option D, V0 by 5. Let us see how to solve this problem. We are given a particle in an one-dimensional infinite potential well with its walls at x equals to 0 and x equals to L. In addition to that, we have a perturbed potential that is varying from x equals to 0 to x equals to L in that system. We are asked to find the first order energy correction to the energy eigenvalue of this particle in that infinite potential well in presence of the perturbed potential. In order to solve this problem, we will use the time-independent perturbation theory. In time-independent perturbation theory, we first solve the unperturbed system to find the eigenstates and the energy eigenvalues. Then we take the expectation value of the perturbed potential with respect to the unperturbed eigenstates or the wave function of that system to find the first order energy correction in that system. So let us see what is the unperturbed states in this case. So this is very well known problem, that is a particle in a infinite potential well which can be exactly solved by using the Schrodinger equation. So by solving the Schrodinger equation, we can find the eigenstate or the eigenwave function of this system, and this is given by psi n x equals to root over 2 by L times sine n pi x by L, where n corresponds to the nth state of this particle in that infinite potential well and L is the separation between the walls in that system. We already know about the wave function or the eigenstate of the particle in the unperturbed system. Now we will include the perturbation which is varying linearly from x equals to 0 to x equals to L. So the perturbed potential will have the form a plus bx, which is the equation of straight line. So we will apply the boundary conditions of the perturbed potential to find the coefficient a and b in that equation. So at x equals to 0, this perturbed potential is 0. So basically it will give a equals to 0. At x equals to L, this perturbed potential has the value V0. So we'll have V0 equals to B times L, and our A is 0 from the first boundary condition. So basically it will give P equals to V0 by L. So if we put that A equals to 0 and B equals to V0 by L in that equation, then we will get the perturbed potential as Vpx equals to V0 by L times x. Till now, we already know about the wave function of the unperturbed system and the form of the perturbation or the perturbed potential in that system. Now, we have already discussed how to find the first order correction to the energy eigenvalue in presence of the perturbed potential. So, this is actually we have to take the expectation value of the perturbed potential with respect to the unperturbed wave function of that system. So this is given by En1, which is the first order energy correction, equals to this expectation value of the Vpx with respect to the psi n x, which is the unperturbed wave function of that system. So now our psi nx is basically root over 2 by L times sine n pi x by L, and our powder potential Vpx equals to V naught by L times x. So we will just convert this bracket notation to the integration form. So this will basically give your Vpx times psi n square times dx and integration over 0 to L. So if we just put the psi nx and Vpx in that integration, so we will get 2 by L times V naught by L times integration 0 to L x sine square n pi x by L times dx. Now we will take these 2 inside the integration. So this will basically give this 2 sine square n pi x by L. Now we know 2 sine square theta equals to 1 minus cos 2 theta. So we will just apply that trigonometric formula here. So this will give first order integration En1 equals to V naught by L square times integration 0 to L x times 1 minus cos 2 n pi x by L times dx. So basically now this integration is divided into 2 parts. So this will give V naught by L square times integration of 0 to L x dx minus integration from 0 to L x cos 2 n pi x by L dx. Now from the previous equation we have to perform two integration. One was integration x dx from 0 to L, and another one was integration 0 to L x cos 2 n pi x by L dx. So for the first integration we will have V naught by L square times x square by 2 from 0 to L, and for the second integration we have to apply the by parts rule. So this will give V naught by L square times x sine 2 n pi x by L whole divided by 2 n pi divided by L from 0 to L minus integration 0 to L sine 2 n pi x by L divided by 2 n pi by L times dx. So this term will basically give V naught by L square times L square by 2, and for this term we will have V naught by L square times 0. So basically for at x equals to L, this will give sine 2 n pi which is 0, and x equals to 0, this whole term x sine 2 n pi x by L will be 0. So effectively it will give 0, and we have to perform this integration again. So this will give L by 2 n pi times minus cos 2 n pi x by L whole divided by 2 n pi by L from 0 to L. So this term will give V naught by 2, and we have plus V naught by L square times L square by 2 n pi whole square times at x equals to L it will give cos 2 n pi, and x equals to 0 it will give cos 0. Now cos 2 n pi is 1 for any integer value of n, and cos 0 is 1. So effectively this term will give 0. So our first order energy correction will be V naught by 2. So our option C is correct for this question. From our solution we found that the first order correction to the energy eigenvalue is option C, that is V naught by 2.